Next important compound of nitrogen is ammonia. Ammonia having a pyramidal structure, lone pair of electron and 3 hydrogen atoms having the same angle with each other as well as equidistant from nitrogen. Ammonia is highly important for life because if we consider the theories, the beginning of life, somewhere these ammonia molecules have played their role for the formation of protein molecules or simple carbon-nitrogen molecules that were further complicated to produce life. And these molecules do exist in many stellar bodies like many of the moons of Saturn. Ammonia is present in small quantities in air and soil, where it is formed by the decay of nitrogenous compound like urea. We are talking about our planet Earth. Here organic matter do exist, and with their decay, ammonia is produced. Simple. Urea through an enzyme known as urease. These enzymes are present in microbes that decomposes this urea into our carbon dioxide and ammonia gas. Many times you see unclean urinaries, very pungent smells start coming up. This pungent smell is nothing but because of ammonia, which produced through the decomposition of urea present in our urine by these microbes using the enzyme urease. On large scale, ammonia is manufactured by Haber's process we just saw. On lab scale, ammonia is obtained from ammonium salts, like we having ammonium chloride. We react it with calcium hydroxide. So basically, ammonium chloride is a salt of strong acid HCl and weak base ammonia. Calcium hydroxide is a strong base. So when we react a salt of weak base strong acid with strong base, so strong acid react with a strong base, we are getting a calcium chloride as a salt, water, and ammonia is replaced or displaced from the compound by the strong base. Similarly, in case of ammonium sulfate, we react it with the sodium hydroxide, strong base, H2SO4 and ammonia. H2SO4 is a strong acid. Ammonia was a strong weak base. So ammonium sulfate having is a salt of weak base strong acid. When it reacts with a strong base, weak base like ammonia is replaced. This comes out. We are getting a sodium sulfate and water with ammonia coming out from the reaction. Properties of ammonia. First, ammonia gas is highly soluble in water. Its aqueous solution is weakly basic due to formation of hydroxyl ions. As we know, ammonia got a lone pair of electrons. Those lone pair of electrons can accept protons from water to make an ammonium ion, and that leaves behind hydroxyl ions, which makes the solution basic. That's what we saw. Ammonium ion formation, which solubilized in water, leaving the hydroxyl ion, which makes the solution basic in nature. Now, lone pair of electrons of nitrogen in ammonia, they can be complex with many metal ions, like we having a copper ion in copper sulfate. If we pass ammonia gas in that, it will making a deep blue color copper complex. Silver chloride, which is a colorless, and silver chloride precipitate, it's white in nature. So if this precipitated silver chloride we pass the ammonia gas, what happens? It will solubilize this precipitate, making a ammonical silver complex, which is colorless again. Ammonia having a widespread uses, first as a fertilizer, like we having ammonium sulfate, ammonium phosphate or ammonium nitrate. These are important fertilizers which are having a huge impact on a agrarian economy like us. So we are using these nitrogenous fertilizers, and these fertilizers really played their role for achieving green revolution. Another use of ammonia is as a refrigerant. In space station, it is very important to maintain the temperature inside to a comfortable level. So International Space Station active thermal system pumps fluids through their closed loops, a liquid ammonia coolant loop along the station's main troughs. This is the station's main troughs that keeps the station electricity and solar panels cool. So this liquid ammonia they are using for cooling these photovoltaic cells as well as for keeping the station cool. These are the external loops where ammonia is used as a coolant that takes away the heat from these panels and keep them cool. Otherwise, these will be destroyed and there will be a power blackout in the whole International Space Station. Here you see ammonia is used as a coolant. So this is just one of the examples where ammonia is used as a coolant. Now we'll talk about oxides of nitrogen. First, nitrous oxide, which is also known as a laughing gas, and its another side is it is a global warming gas, greenhouse gas. Nitrogen dioxide is used to produce rocket fuels and explosives. So these are the few uses of nitric or nitrogen oxides. But they have a negative side as well. Nitrogen oxides, in particularly in diesel engines produced, they can create havoc in cities through environmental pollution. What happens? These nitrogen oxide, NOxes, they react with the sunlight and other chemicals to make a smog, which is very dangerous to health. Nitrogen oxides and sulfur dioxides can react with the atmospheric moisture to create acid rain. That is the reason most of the refineries has been pushed out of the Agra city, because these acid rains were highly or deadly for the marble epitome. This architectural beauty was under threat because of these oxides of sulfur. Their sulfur dioxide was more of a concern than nitrogen oxides, but definitely in cities, nitrogen oxide is also responsible for acid rains. Let's first discuss certain nitric or nitrogen oxides. First is N2 nitrous oxide. Its formula is NNO. It is produced through decomposition of ammonium nitrate, N2O and water. Next is nitric oxide or nitrogen monoxide. This is produced through a reaction of sodium nitrite with ferrous sulfate in the presence of H2SO4. We are getting the ferric sulfate and sodium hydrogen sulfate, nitric oxide as a what is the product was here. Dinitrogen trioxide is having a structure of NN, and one nitrogen atom is bound to two oxygen atoms and one to single atom only. And in this case it is produced by the reaction of this nitric oxide with nitrous or say N2O4 or NO2. When we react the N2O4 with nitric oxide, we are getting dinitrogen trioxide. Nitrogen dioxide. It is produced through decomposition of lead nitrate at high temperatures. Dinitrogen tetraoxide is produced through equilibrium of nitrogen dioxide to give us nitrogen tetraoxide. When this nitrogen dioxide is produced, if we cool it to a desired level, the equilibrium will shift towards the formation of dinitrogen tetraoxide. Dinitrogen pentaoxide is produced through reaction of phosphorous pentaoxide with nitric acid. That gives us the HPO3 and N2O5. Remember, nitric acid reaction is phosphorus pentaoxide. The structure of N2O5 is having a angular oxygen which binds two nitrogen atoms, and each nitrogen atom further bound to two oxygen atoms. Nitrogen dioxide contains odd number of valence electrons. So when we cool it sufficiently, it will tend to form dimer, which is N2O5, which got even number of electrons. So we can see it will try to make an even number of molecules or even number of electrons. That's why it try to dimerize. Nitric oxide. Nitrogen forms oxoacids such as hyponitrous acid H2N2O2, nitrous acid HNO2, or nitric acid HNO3. Among these, nitric acid is most important acid of nitrogen, having this structure. This is a hyponitrous acid, nitrous acid, and this is structure of nitric acid. Nitric acid. Commercially, nitric acid produced through Ostwald's process. Like on lab scale, we can produce it by the reaction of sodium nitrate with H2SO4, which is an acid. We are getting the nitric acid and sodium hydrogen sulfate. Now, commercially, we get it through Ostwald's process. First step is catalytic oxidation of ammonia using atmospheric oxygen. Catalyst will be platinum rhodium catalyst at high temperatures and high pressure. So we are getting nitric oxide. In second step, nitric oxide combines with oxygen further to give a nitrogen dioxide. So we see oxidation further of nitric oxide to nitrogen dioxide. In third stage, nitrogen dioxide is controlledly dissolved into water to give a nitric acid. and in this process NO is produced, which is further used in the second step. This is a basic layout of Ostwald's process, three-step process to create nitric acid from ammonia. Concentrated nitric acid is a strong oxidizing agent and reacts with the most metals except gold and platinum. It reacts simply with zinc to make a zinc nitrate. And if we put a dilute nitric acid, we are getting a nitrous oxide. In a concentrated nitric acid, we are getting nitrogen dioxide. So even the concentration or the kinetics in case of dilute acid and strong acid changes to give us a different outputs. Here, iodine get oxidized to iodic acid, carbon got oxidized to carbon dioxide, sulphur got oxidized to sulphuric acid, phosphorus get oxidized to phosphoric acid in the highest possible oxidation state, sulphur 2 plus 6, carbon 2 plus 4, iodine 2 plus 7. So nitric acid is a good oxidizing agent, and output in all these will be nitrogen dioxide, which is in plus 4 oxidation state. In nitrate it is in plus 5 oxidation state. This is the structure of iodic acid, HiO3, sulphuric acid, H2SO4, phosphoric acid, H3PO4. Another important use of nitric acid is brown ring test for the nitrates depend upon the ability of ferrous to reduce nitrates to nitric oxides, which further reacts with the hydrated our ferrous ions to form brown colored complexes. This is a chemical reaction, nitrate, which oxidizes the ferrous to ferric, and these ferric ions further they coordinate with water and nitric oxide formed in a chemical reaction to give us a complex, brown complex. That's what happens. We put a ferrous sulfate, freshly prepared ferrous sulfate, and we are getting this ring kind of structure, which is a test for nitrates present